Okay, one problem with electromagnetism is that it's hard to get some demonstrations and to find stuff to play with. But there are some nice simulations on the internet that you can use freely. One of them is this one, the falstadt.com. Well, I will just write it for you. Okay, where you can just go for math and physics applets. And well, there are simulations about many physics phenomena, from mechanics to electromagnetism, quantum physics, etc. You can just go over the page. Now, one of the simulations is this one, the 3D electrostatics applet, where, if you remember, on last week we were discussing the electrostatic phenomena. We had this charge distribution. We said that, okay, there's this force between charges, and rather than taking this action at a distance, we said, okay, let's just imagine that there are fields. If you have a charge, there's a field, it creates that fills all of the space. And if you put another charge somewhere else, it only fills the field at that point. And to show these fields, we prefer to use what we call the electric field lines. Here, for example, is an example where you have the electric field lines of a point charge. So as you can see, they're just pointing radially outward. And some more interesting stuff would be, let's say, not a point charge, but we also studied this dipole, where we had one positive charge and another negative charge, and this is how the field lines look like. Now, rather than the field lines, you can prefer to see the field vectors. So as you can see here, well, it's kind of hard to see on the projector, but here there are some vectors pointing in that direction, so that already tells me that, at least in this simulation, this is positively or negatively charged. This is positively charged because the electric fields are pointing away from that charge and towards this charge, so the field lines are moving in this direction. And if you can just rotate it to see how it looks like at different points. Now, of course, the number of lines that you see here, or the number of vectors that you see here, is completely arbitrary. It's just a sample of the points. Some points are just chosen randomly, well, in this case, with a pattern. And only at those points the vectors are shown. But at every point in space, you have an electric field vector, and there is an electric field line that passes through that point. Now, we had also discussed some conductors. Let's see. Now, for example, here, okay. Now, where we have this, there is also another simulation of a conducting sphere and the point charge. So this is the field electric vector fields. Let's show the lines, which are more interesting, easier to identify. Now, as you can see, now when you draw these field lines, since this is a conductor, we had already discussed that the field vectors, field lines have to be perpendicular on the surface. So as you can see, this just goes perpendicular to the sphere. This is perpendicular, this is perpendicular. Now I look for, if you remember, we had studied the ring. Unfortunately, there is no ring here, but there's something similar, just two lines. So here we have two lines. Here there is one line, here there is another line. They have the same charge. Well, if you put two more lines over here and over there, it more or less looks like the sphere, as a ring. You can just imagine rotating these lines to obtain your full ring. So let's see how it looks like. So this is where one line, well, this diagram from this perspective, you can just imagine that we have a ring and we cut it through the middle. And this is how the electric field lines would look like. Of course, there is no field line that's going straight. There is one field line coming from this side. It goes almost horizontally and goes up. There is another one that goes almost horizontally and then down. This is not a continuous line. So this is what happens if you feel the intensity. Oops. So you see that there are all these lines. Since they are both positively charged, the field lines will be leaving from both of them. But as they go towards the other one, they just bend up. And in the middle, if you increase the intensity, it just appears as if there is a line that goes straight, but it doesn't really exist. This is just to help you visualize how these electric field lines look like. Any questions? Okay, before we start, do you have any questions about what we had done last week? We were discussing the charge concept, the force between the charges, and then we had this electric field, which feels all over space. And we said that this field has nothing to do with the strawberry fields. And we were discussing how to draw the field lines of, we had the example of a dipole, 2-point charges of equal magnitude, opposite sign. We had the electric field lines of two charges of opposite sign but different magnitudes. Any questions about those? Yes. Well, if we have, let's say, a positive charge over here, and let's say we have a conducting sphere over there. Now, we know that close to the positive charge, the electric field lines should be just radially outward, because close to the positive charge, the electric field of this positive charge will be almost infinite. It will be the dominant one that determines the direction of the field line. So it will just leave radially outward in all directions. And as they go towards my charge, it will just bend to make sure that it is perpendicular. This is a conductor. Well, we had said that if the electric field line is not perpendicular to the surface, that means it has a horizontal component, a component that's horizontal to the surface. But that means that component will exert a force on the electrons, which will be horizontal to the surface. So the electron will be free to move horizontal to the surface. That's the definition of a conductor. But since we are studying only static cases, in statics, it means electrons inside my conductor are not moving. So in statics, it has to be perpendicular. But we will study electrodynamics, for example. In electrodynamics, if we have the charges are moving around, if the fields are time dependent, in that case, it doesn't have to be perpendicular. But in electrostatics, it has to be perpendicular to the surface. And if you put some negative charge over here, the only difference will be the lines will point in the opposite direction. Okay. I didn't done. Okay. Now, I mean, if when the, you see, if you consider the forces acting on the electron, just imagine some piece of a conductor. This is a conductor. And the properties of the conductors are such that the charges inside the conductor can freely move inside the conductor. So if you take a piece of a metal, for example, in the metal you have the electrons that will be free to move around. It can move like this, move in that direction, etc. But it is not free to go out of the conductor. The conductor exerts, if the electron tries to move out of the conductor, then the conductor will exert some force on the electron to pull it back. So the conductor itself exerts a force on the electrons that is perpendicular to its surface. So if you are exerting, if I understood you correctly, your question is that, okay, we have these electric field lines perpendicular to the conductor at this point. It means there is a net force acting on the electrons in the conductor in the direction of the electric field, right? In the opposite direction. That's your question. So if you just imagine some electron here, it will be feeling two forces. One, the force due to this charge, plus there will be some additional force due to the conductor. And these two forces will cancel each other. But the force of the conductor is perpendicular to the surface. You can just think of it as a kind of a normal force. It doesn't have a horizontal component. So it can cancel this. When you sum up these vectors, it can cancel a vertical force created by the charges outside my conductor, but it cannot cancel a horizontal component of that force. No. Whatever conductor you have, in fact, if you look very close to a point, it's horizontal. It's flat, whatever the shape of the conductor is. Now, here, of course, if the electric field is very huge, you create a huge electric field, then you will start ripping off electrons from the conductor. If the forces that you exert on the conductor due to these external charges is larger than the conductor can exert on the electron to keep it there, in that case, the electron will just get off the conductor. And here, again, we are assuming that we are not looking at those cases. The electric field is not that strong. What do you mean? Well, of course, there are a few possibilities. Is this a neutral conductor or a charged one? Is it grounded or not? Let's say it's an isolated conductor. That basically means that, well, if we put some positive charge over here, negative charges had accumulated over here. So I have positive charges on the other side. So the electric fields will just leave from here. Again, they will be all perpendicular. And at this point, they don't overlap. I mean, there is a point over here where there will be no electric field. electric field will be 0. Well, since my system is static, it is not changing. This is how my system will look like at all times. No. Now, when I put bring this charge initially, I have created some currents inside, some motion of the electrons. But I have waited long enough so that all the electrons in the conductor are now at rest, on the average at least. Even if you put an electron over here, let's study that. Let's study how particles move in an electric field. Well, this is kind of still static in the sense that the fields are static. We have a single charge that's moving around under the influence of these static fields. I mean, if you have any questions, I mean, before looking at that motion of particles, well, that's an alarm. Oh, I'm not saying something wrong. So now, before we start on studying how the charged particles move under static electric fields, if you have any questions about this, let's first discuss them. Well, let's build an electron gun. The simplest electron gun would be you take some plate, a conducting plate. You take another conducting plate, make a hole somewhere, and connect it to a battery. We will study batteries later on in more detail, such that you charge them. Let's say this one positively, this one negatively, this one positively. And if you put some electron over here, so there's an electron over there. So what will be its motion? Now well, of course, what's the direction of the electric field inside these two plates? From the positive to the negative. And so what is the direction of the force acting on the electron? Towards the positive side. So it will start accelerating, and then it will just leave. This will be its speed when it leaves these two plates. Now, we had already studied this example of a single plate. We had a charge density sigma. If we assume that this is positively charged, and we had already found out that the electric field here, let's say if this is the E, this will be minus E. It will be pointing in the opposite direction. And the magnitude of this electric field was sigma over epsilon 0. This is what we had calculated last week. Now, if you put two of them side by side, so here we have some positively charged plate, and here we have a negatively charged plate. Now, the question is, what is the electric field everywhere in the space? What is the electric field here, here, and here? Now, we had already seen the superposition principle, which says that if you have two different charge distributions, they will each be creating their own electric field, and at a given point, the total electric field will be the electric field created by both of them. So if you want to find the electric field at any point, it will be the sum of the electric field created by the positive charges plus the electric field created by the negative charges everywhere. Now let's split our region into 3 parts. My region 1, my region 2, and my region 3. So that I can study the electric field at each one of these regions separately. And let's take this as my, let's say, z-axis. So region 1. What is the electric field created by the positive charge? Well, it is in the minus z direction. Magnitude. Sigma over epsilon 0. Two epsilon 0. Electric field in the first region created by this negative charge distribution. Remember, the electric field always points away from the positive charges and towards the negative charges. So at this point, these negative charges will create an electric field towards the negative charges. So it's in the plus z direction. And its magnitude is again sigma over 2 epsilon 0. So the electric field in the first region is just the sum of these two, which is 0. There is no electric field in the first region. Of course, there are a few assumptions that we have made. We had assumed that these plates are infinitely long. Unless these plates are infinitely long, this will no longer be true. And just also note that when I'm considering this E minus, I just ignored that I just ignored this plate, this charge distribution. It doesn't affect E minus. There was a question asking, okay, if we have some charge over there, we are calculating the electric field over here, and we put something in between. Does it influence? Well, as long as, well, it doesn't influence anything. It might create its own electric field, what you put in between, but it will not affect the electric field created by that other charge distribution. Questions? Okay, there was one question who was asking, if, let's say, there's a charge sitting over there, I want to calculate the electric field over here, and you put something in between us. Let's say you put this table in between us. Does it affect the electric field at this point? The answer is yes and no. It doesn't affect the electric field created by that charge over there. It is not affected by the presence of anything inside. But what you put in between can create its own electric field. So if you want to calculate the electric field here, you have to sum the electric field created by that charge over there and the electric field created by what you put in between. And that is basically what we are also doing over here. The electric field created by this minus charge at this point is not affected by the presence of this additional plus charge in between, positive charge in between. So this E minus is calculated as if this just doesn't exist. But of course, this thing that we put in between creates its own electric field. And so we also add that one up to calculate the net electric field in the first region. No. Whatever you put over here, whether it's a conductor or an insulator, it will not affect anything. Of course, the difference between an insulator and the conductor will be if you, let's say that there's some charge distribution over here, and you want to calculate the electric field that you will feel. Now, if you put some insulator over here, the charge distribution of the insulator will not change. So this thing will have no effect on you. But if you put a conductor here, the charge distribution of this conductor will also be modified, and hence it might influence the total electric field that you will feel. Now let's look at the electric field in region 2. Okay, what is the electric field created by the positive charge? In the positive or negative? It's in the positive direction. And the negative charge? Positive or negative? It's always towards the negative charge, so it will be in the positive direction. Just, I mean, if you want to find the direction of the electric field, just imagine that you put some positive charge over there. So if you put some positive charge over there, it will feel a force towards the negative direction, negative charges, so it's in the positive Z direction. So the total force, total electric field in this region 2 will be in the positive direction, sigma over epsilon 0. And finally, in region 3, this one. The electric field created by the negative charge. If you just imagine some positive charge, it will feel a force towards the negative charge that is in the negative Z direction. Remember, I'm looking at some point over here. So it's in the minus Z direction. The magnitude is sigma over 2 epsilon 0. And the electric field created by this positive charge plus Z sigma over 2 epsilon 0. So the total electric field in region 3 will be 0. They have no effect. No. These are not lines, by the way. These are just infinite planes. Yes. If they are finite, you will have electric field that changes with distance. So let's see, if you sum up the electric fields, at this region, we found that the electric field is 0. In this region, we found that the electric field is again 0. Well, that's basically because the electric field of an infinite plane is not affected by the distance. So although if I choose some point over here, it is closer to the negative charge than the positive charge, since distance doesn't have any effect for the electric field created by an infinite charges or infinite planar charge distribution, it doesn't have any effect. So their magnitudes are still the same, but in opposite directions, so they cancel each other. In between, we found that the electric field was sigma over epsilon 0 in the Z direction. This is just a uniform electric field from the positive charge to the negative charge. Questions? So let's go back to our original question. So we know that in between the magnitude of the electric field is just sigma over epsilon 0. Sigma being the charge density on these plates. Now, of course, the plates are not infinite. There's a hole in this plate. So these will all give some modifications to this expression for the electric field, but they will be small. And if you want to, this is an electron, this is a simple scheme of an electron gun which are used in accelerators. if you want to actually build this thing and put it in an accelerator, in a particle accelerator, you have to take into account that this is something finite, there is a hole over there. But for our purposes, for just to get a basic idea about how this works, this will be enough. So what is the force that the electron feels? Remember, the force of a charge in an electric field is nothing but Q times the electric field. So for an electron, this is minus E. Well, the electric field, again, let's just assume this is the Z direction, is in the minus Z direction, sigma over epsilon 0. And this is in the Z direction, E sigma over epsilon 0. So the electron in the system feels a force pointing towards the positive plate. And this is a constant force. So what is the acceleration of our electron? We know the force over mass from Newton's second law. So this is Z times E sigma over mass of the electron, epsilon 0. And, well, this is a motion with constant acceleration. You can just write down the position as a function of time, 1 over 2 AT squared, if you assume that initially it is at rest, and this is the 0 point. This is in the Z direction, E sigma 0 to twice T squared. So in fact, such a setup would allow you to determine the E over M ratio for the electron. If you can determine how long it takes for the electrons to reach from this point to the other plate by just putting some detector on this hole, you can measure the time T. Epsilon 0 is just a constant. Sigma is something that you prepare. You know that you should know this value. 2 is just a constant. The only unknown here is the electric charge divided by the mass of the electron. So you can determine the electric charge over the mass of the electron through such a setup by measuring this time T. Now, in this case, when we put the charge at a point, its trajectory followed our electric field lines. But this will not be in general true. You see, the thing is, the force is in the direction of the electric field lines. That is, the acceleration of the charged object is in the direction of the electric field lines. But the particle need not move in the same direction. It's only the acceleration. Now, let's do another example. Let's just imagine this time we have these two charges, two plates. This is, well, we can do two examples. This is negatively charged. This is positively charged. Ignore gravity. And you just send some charge Q in between these capacitors. Well, again, depending on the charge Q, the force it will feel, say this is plus sigma, this is minus sigma. Let's call this axis the Z axis. So the electric field will be in the negative Z direction or positive Z direction. It will be in the positive Z direction. Sigma over epsilon 0. So we know the acceleration of the charge. This is QE over M. Q sigma over M epsilon 0. This is the acceleration. Again, our particle just makes motion with constant acceleration. And we have already studied in the first semester how such a particle moves. This position as a function of time will be just 1 over 2 AT squared. And depending on whether it's positively charged or negatively charged, it will either move up in a parabola or move down through a parabola. Now let's consider a third example. This is the Millikan experiment. It was one of the first experiments which proved that the electric charge is quantized. So suppose you have again these two parallel plates. One is positively charged. The other one is negatively charged. And you just put some charges in between. Let's say some charge Q moving with, let's say, you can put some charge Q mass M. You might give them some initial velocity or not, it depends on your setup. Now let's calculate the net force acting on it. This is again Z. The total force acting on this one, well, this time it will have two components. One, the electric force, and the other one is the gravity. We are not ignoring gravity. Now in Millikan, what he used was he just used this, you have these perfume, how do you call them? Sprays. They just create very small water droplets. And he just let them pass through a strong electric field, which ripped some electrons, or gave it some electrons, so that they became charged. And the droplets that had the correct mass and the correct charge had the total force equal to 0. QE plus mg. This is equal to Q. Well, the electric field is minus sigma over epsilon 0 z hat. So this is equal to minus Q sigma over epsilon 0 minus mg. In the z hat direction, this was equal to 0. And this is only true if Q is equal to minus mg epsilon 0 over sigma. No, sigma is not a vector. No, okay. Well, where is the Earth? Okay, so it's in the minus z direction. I'm assuming that this is Earth. So I have these two plates. This is positively charged, this is negatively charged. So the gravity, acceleration of gravity is pointing downward. It should be negatively charged. You see, there is this minus sign over here. Now, it's not necessarily equal to 0. If the total force is equal to 0, or if the charge has this value, the droplet will not accelerate. So if you actually do this experiment, when he did this experiment, of course he had some holes over, he had a hole over here to put the droplets in between. And when he did this experiment, he actually could see some droplets hanging in the air. So since there are some droplets hanging in the air, it told Millikan that the charges of that droplet has to be given by this expression. Well, sigma is something he prepared, so he knows the value of sigma, gravitational acceleration, he knows epsilon 0, he knows the mass. The mass he doesn't know, but he can just, by looking at this system, by the droplets, through a microscope, he could measure their size. If you know the size, you know the density, so you know the mass. So he knows the masses of those droplets that were hanging in the air, so he could determine the charges of each one of the droplets. And he saw that they were actually quantized. Yes. Well, if the charge is positive, both the electric field and the weight, they are pointing in the downward direction, so they will not. The net force can never be zero. So in the setup, at least, the charge has to be negative. Otherwise, it will not hang on in between. I mean, this is the total force is not necessarily zero. But for the droplets for which the total force is equal to zero, they have this charge. There are all other droplets, probably some of them have the opposite sign of their charge, so they will just keep accelerating downward. Some of them will have a charge larger than this one. They will just accelerate upwards. But there will be some, and that's what he saw in the experiment. There were some droplets just hanging in the air. Now, Newton tells us that if something is not accelerating, it means that it is the net force acting on it is zero. So if the net force, there are two forces acting on these droplets hanging in the air, the electric force and their weight. So they have to cancel each other. And so the charge of these droplets should be given by this expression. Only for those droplets that are hanging in the air. And since the electric force is much, much stronger than gravity, these droplets, they tend to have just one or two electric quanta. One more electron or one less electron. And he could determine, well, by just choosing the value of epsilon 0, he could determine the charge of the electron. Questions? Now, for example, in this example, let's say the previous one, the charged particle is not moving along the electric field lines. The electric field lines here are perpendicular, vertical. But if this is, let's say, negatively charged, the trajectory of this object will be a parabola. It's not following the electric field lines. Other questions? Let's do another example then. Let's just imagine we have a region of space where we have some uniform electric field. We can just create it by just, let's say, putting two infinite plates, almost infinite plates, and then in between we have a uniform electric field. And in this electric field, I just imagine that I take just two charged spheres. Let's say one of them here, positively charged, one of them here, negatively charged. They are connected by a rigid rod. This is plus Q, this is minus Q. So this is the system I have. Now the first question, what is the net force acting on this system in this configuration? No gravity, ignore gravity. Zero or some charge. Why do you say so? The system has no net charge, so your friend says that there is no net force. Well, I mean, if the electric field was not uniform, although the system doesn't have any net charge, it would still be a net force acting on it. But since the electric field is uniform, your answer is right for this special system. Now, why is it so? Let's just imagine, what is the force acting on the negative charge? Let's say this is the x direction. The force acting on this negatively charged sphere. It's in the minus x direction. What about the force acting on this positive charge? Well, remember the force is Q times E. So for a positive charge, Q is a positive number. So if you multiply a vector with a positive number, it points in the same direction. For a negative charge, you are multiplying a vector with a negative number. It will be pointing in the opposite direction. So this will be for the negative charge, the force is in the opposite direction of the electric field. For the positive charge, the force is in the same direction as the electric field. And since the magnitudes of the electric field at the position of the negative charge and at the position of the positive charge are identical, the net force acting on the system, these two forces have the same magnitude, but they're just pointing in opposite directions. So the net force is still zero. Now, if the electric field is not uniform, this will not be true. So the total for F is equal to minus F prime. So the total force is F plus F prime, which is equal to 0. Now the next question would be, what is the net torque? This is we will discuss after the break. Now, any questions before you go for a break? We will discuss what happens later on. There was a question over there. Well, of course, if you want to calculate the torque, you have to calculate the torque relative to a point. In this example, calculate the torque relative to the center.